Good morning, everyone. Welcome to quarterfinals in the webinar. So today we are very happy to have Henrik Wirzenius, and he is speaking on closed ideals in the Banach algebra of compact by proximal operators. Henrik?
Thank you. Thank you for the introduction and for the great opportunity to speak here in this webinar, and also thanks to everybody that is joining online. So let's go right into it. So, if it works. Yeah, okay. So I will speak about the compact by approximable algebra, and for the definition, let's just recall the standard notation. So K of x will denote in this talk the Banach algebra of compact operators on a Banach space X. The Banach space X can be either real or complex. It doesn't matter for our results. And A of x denotes the class of approximable operators on X, which is per definition the closure of the bounded finite rank operators. Well, A of x is a closed ideal of K of x, so we can take or the quotient algebra is well defined, K of x divided by A of x, and that is what we call the compact by approximable algebra, and we denote it with this script AX. And well, I will usually just speak about the quotient algebra in this talk. This is a Banach algebra with the usual quotient norm. So the norm of an element t plus ax is the distance of the compact operator t to the approximable operators. And the aim of this talk is to present different kind of examples of Banach spaces for which this quotient algebra, compact by approximable operators, has non-trivial closed ideals. And this is based on a recent preprint. You can find it in the archive. It's written together with Hans-Olav Tylli, who is also attending this seminar today. So if you want to know, go more into details and see more examples and results, please go and see this preprint. Now, for the first fact about this quotient by approximable algebra, let's just recall what a radical Banach algebra means. So a complex Banach algebra A is radical if the spectrum of every element is trivial. And here the spectrum is computed in the unitization of A. And well, because the spectrum is always trivial, you can't use any spectral theory for studying radical Banach algebras. And a fact that can be found in the book by Garth Dales on Banach algebras and automatic continuities is the fact that this quotient algebra AX is a radical Banach algebra. Well, I mentioned that the underlying Banach space can be either real or complex. If it's real, then this quotient algebra is also a real Banach algebra. Then we simply just mean by the radicality that the real spectrum of every element is zero. And this is true because the classical Riesz-Fredholm theory is independent of the scalar field. Okay, next I will briefly talk about the motivation why we should study this quotient algebra. So first of all, one can argue that it's in a way a very concrete, typically non-commutative radical Banach algebra. And concerning the topic of today, closed ideals, Well, they are closely related, as we will see, to closed ideals of the compact operators. Also, in some cases, closed ideals of the bounded operators, L of x, where the closed ideal lies strictly between the approximable and the compact operators. The third point is that this quotient algebra is very poorly understood. I mentioned it's radical, but it's also very much connected to Banach spaces failing the approximation property, which makes it a difficult object to study. And almost nothing exists in the literature on this quotient algebra and its properties. And a final point that perhaps is good to have in the back of the mind, there is an open problem in Banach algebra theory, namely, is there a topologically simple radical Banach algebra? So what that means is that is there a radical Banach algebra that has non-trivial products and no non-trivial closed ideals? Okay, I mentioned that the quotient algebra is related to the approximation property, so let's briefly recall the definition of the approximation property. So a Banach space X has the approximation property AP if for every positive epsilon and every compact subset K of X, there is a bounded finite rank operator T on X such that the supremum taken over all elements X in K, the norm of Tx minus X is less than epsilon. So this means that the identity operator can be approximated by finite rank operators uniformly on compact subsets on X. Now, the following classical characterization of the approximation property kind of shows why it's relevant to the quotient algebra. So Grothendieck show that a Banach space X has the approximation property if and only if every compact operator from Y to X are approximable, and this has to hold for every Banach space Y. And as a consequence, if X has the approximation property, then K of X equals A of X, which means that the quotient algebra AX is trivial. And thus it can only be non-trivial within the class of Banach spaces failing the approximation property. And let me also mention this open question about the converse. So if K of X equals A of X, does X have the approximation property? So this is an open question that I guess was first formally stated in the first book by Lindenstrauss and Safriri. Okay, let's go to some early results on the quotient algebra. So there is a couple of papers from the 70s that have explicitly studied the quotient algebra. More precisely, they have shown that in some instances it's non-trivial. First of all, I have to recall that that for the classical sequence spaces, you can always find a closed subspace failing the approximation property. Of course, P cannot be 2 because a Hilbert space cannot have closed subspaces failing the approximation property. And for let's just mention the history here. So the case C0 was solved by Parenflo. So this was the first example of a Banach space failing the approximation property. And soon afterwards, Davy showed that for P bigger than 2, there is a closed subspace of LP failing the approximation property. And a few years later, Jankowski showed that the same is true for P less than 2. Now here is a result on the quotient algebra. So Fred Alexander, soon after the example by Davy, showed that if P is bigger than 2, then there is a closed subspace X of LP, so that the quotient algebra is non-trivial. Okay, this was also mentioned in the paper by Alexander, that this can also be deduced by a compact factorization result of Fig L earlier in the 70s. But I guess this paper by Fig L came before the result by Davy. A few years later, 2 years later, Batchelis came with a kind of a general result concerning the quotient algebra. So if we have a Banach space E that has the bounded approximation property, and we assume that E is isomorphic to the direct sum E plus E. So for instance, E can be a classical sequence space. And now assume that this E has a subspace that fails the approximation property. Well, then there is another closed subspace zeta of E containing this subspace failing the approximation property, containing it as a complemented copy, so that the quotient 8 zeta is non-trivial. And now, if you combine this recall thing here with the Batchelis result, it implies that for every p not equal to 2, there is a closed subspace X of LP, and also of C0, with so that the quotient algebra is non-trivial. And here also a historical note, so the case C0 could also be obtained by an earlier result. So this is a classical result by Tertio-Glue, that any compact operator factors compactly through a closed subspace of C0. Now, as a last slide in this introductory part, I will mention some unpublished notes that were written by Garth Dales in 2013. So he wrote notes and sent them to some of his colleagues, I assume, and also to Hans Olav, where he had collected facts and results about this quotient algebra, and also some very interesting open questions. So, for instance, concerning the size of the quotient algebra, can we have a Banach space X, of course, without the approximation property, so that this quotient algebra is finite dimensional? And on closed ideals, there was, for instance, the following question. So well, what can one say about the structure of the family of closed ideals of the quotient algebra? Are they always or sometimes totally ordered? Large nested collections of closed ideals? Can we have infinitely many closed ideals? And so on. And then there were some more questions, the more Banach algebraic flavors about factorization and amenability and so on. But one could say that the main kind of message was that one should know more about this quotient algebra that was known at that time. Okay, and here I will mention two papers by me and Hans Olav. So the first one concentrates on the question about size, TW1. So there we provide examples of Banach spaces where this quotient algebra is large, so it's infinite dimensional. Yes, and here is the paper, the preprint that was already mentioned. So TV2, where we provide examples of Banach spaces where we have non-trivial closed ideals of the quotient algebra. Okay, now we go to the closed ideals. So here is a starting point. So first of all, if we look at closed ideals of K of x, I will say that a trivial closed ideal is either 0, the whole K of x, and also the approximable operators. So they are always a closed ideal of K of x, and we will simply call them also trivial. Now for an arbitrary Banach space zeta, if we denote the quotient map from K of z to the quotient algebra by K, then we have this observation that if we have a non-trivial closed ideal of the compact operators K of z, then the image in the quotient map will be a non-trivial closed ideal of the quotient algebra. And also vice versa. So if we have a non-trivial closed ideal of the quotient algebra, then the inverse image of the quotient map will be a non-trivial ideal of the compact operators. So we have a one-to-one correspondence between non-trivial closed ideals of the quotient algebra and non-trivial closed ideals of the compact operators. And why I mentioned this is that in many cases it's easier to find closed ideals of the compact operators, and then we get closed ideals of the quotient algebra with the quotient map. Okay, I have listed two kind of strategies for finding non-trivial closed ideals of the compact operators. So the first one is perhaps a bit vague, but if you somehow can define internal conditions, which will then provide closed ideals strictly between the approximable and the compact operators. So here the challenge is to kind of knowing how to define this condition, but also you have to check that you really get a closed ideal. And a bit of a warning. So in this case, if you have a non-trivial closed ideal of K of x, it may not always be an ideal of the bounded operators. Another way to find non-trivial closed ideals is to use operator ideals. So if we can find an operator ideal I, this contained in the compact operators, so that the operator norm closure of I lies strictly between the operator ideal of the approximable operators and the compact operators, then we will get a closed ideal, closed non-trivial ideal of K of zeta for a specific Banach space zeta. So I will just recall, I know this, there has been talks about operator ideals before in this webinar, but let's just briefly recall the definition. So an operator ideal I assigns to every Banach space x and y a linear subspace of the bounded operators from x to y, so that the finite rank operators lie inside this linear subspace, and then the ideal property holds. So for all Banach spaces zeta and w and bounded operators s and t, bounded operators s and u and if we have an operator T that is in this operator ideal, then the product UTS will be in this I set to W. Okay, I will just briefly state why we will get a Banach space and a non-trivial closed ideal of the compact operators. So suppose that we have these 4 Banach spaces X, Y, Z, and W that satisfies these 2 conditions. So the closure of I X to Y is strictly bigger than the approximable operators, and the closure of I Z to W is strictly smaller than the compact operators. Well, then if we take the direct sum of these 4 Banach spaces E, then by the ideal property of these operator ideals, we will get a non-trivial closed ideal of the compact operators of E. And finally, I also have a kind of a third way of finding closed ideals. Well, let's say it would be nice to find these kind of ways, but we don't have. So a question, are there kind of Banach algebraic ways of finding closed ideals of the compact operators? But we don't know if there are any. Okay, next I will briefly talk about this operator matrix notation. So all our examples will be on direct sums of Banach spaces. And if you have a bounded operator U on the direct sum of X plus Y, then we can write this operator as a matrix, as a 2 times 2 matrix where these components, well, the 1, 1 component will be a bounded operator from X to X. The 1, 2 component will be a bounded operator from Y to X, and so on. And an important observation here is that a bounded operator on a direct sum is compact if and only if each of these components in the matrix are compact. And similarly for approximable operators. Actually, this holds for any operator ideal I. That an operator is in the operator ideal if and only if each of the components are in the operator ideal. And we will also use this notation for classes of compact operators on direct sums. So if we have a compact operator on X plus Y written in this matrix notation, if each of the components are in a class of compact operators, well, then we can simply write this class of operators in this way. So this is just to simplify the notation in our first example. Okay, so let's go to our first example where we obtain closed ideals. So this should be a class of examples. So if we have 2 Banach spaces X and Y, such that X has cotype 2 and Y has type 2, then we also need that the quotient algebras AX and AY are non-trivial. Then these classes of compact operators on X plus Y, so I and J, they will be non-trivial closed ideals, the compact operators. They will be incomparable closed ideals. And then, of course, we get with the quotient map 2 incomparable closed ideals of the quotient algebra A X plus Y. And here is a concrete example. So So with a concrete example, I will in this talk mean something that has to do with closed subspaces of sequence spaces. So if we have p less than 2, q bigger than 2, then there are closed subspaces x of LP, y of LQ, so that the quotient algebra A x plus y contains at least 2 non-trivial incomparable closed ideals. And recall this consequence of Bachelys theorem that there are such closed subspaces with non-trivial quotient algebras. Now, a crucial ingredient here for showing that these classes I and J actually are closed ideals is the fact that this 1,2 component here is actually all the compact operators. So in this case, when I has type 2, x has cotype 2, then all the compact operators from y to x are approximable. This is important to show that for showing that these I and J are closed ideals. And I will in the next slide briefly state this as a theorem. The theorem. So if we have the Banach spaces x and y, x has type 2, y has cotype 2, then all the compact operators from x to y will be approximable. And this is independent of any approximation properties. And this is a theorem that comes quite easily by combining two results. One is a classical result by Quappi and Mori that states that if x has type 2, y has cotype 2, then every bounded operator from x to y factors through a Hilbert space. And then there is a result by Camille that states that if we have a reflexive space zeta that has the approximation property, then every compact operator that factors through zeta will be approximable. So combining these will yield this theorem. So if we start with a compact operator from x to y, then the Quappi and Mori results state that we can factor T through a Hilbert space. Well, a Hilbert space is reflexive. It has the approximation property. So this result by Camille says that, okay, T has to be approximable. And a comment that here you can x and y are not interchangeable. So there are Banach spaces x and y where x has cotype 2, y has type 2, and then the compact operators from x to y are strictly bigger than the approximable operators. Okay, here are some related questions to this first result. So, of course, if we can get 2 closed ideals, can we get more in this setting in theorem 1? So one natural question is that is the intersection of I and J a non-trivial closed ideal of the compact operators? And this is true if and only if this component of operators, compact operators from x to y, are strictly bigger than the approximable operators from x to y. So for instance, the case where we had closed subspaces of LP and LQ, then the intersection A intersected with J would be a third non-trivial closed ideal if the compact operators from x to y would be strictly bigger than the approximable. But in this case, we don't know if there are such closed subspaces. Well, here is here is another example that goes in the setting of theorem 1. So if we have P and Q that satisfies these conditions, then we can get closed subspaces X of LP, Y of LQ, so that the compact operators of X star plus Y contains at least 8 non-trivial closed ideals. So 8 is kind of the best we can do at this moment in this class of Banach spaces in theorem 1. Well, then one can ask, can we get other types of examples? And one type of example would be closed subspaces of sequence spaces. So let me recall that if E is LP or C0, then the bounded operators L of E has exactly one non-trivial closed ideal, namely the compact operators. So this is a classical result. Goes back to Goldberg, Marcus, and Feldman, and goes back to Kalkin in the Hilbert space case. So here a natural related question would be, what about closed subspaces of LP? Are there closed subspaces so that the quotient algebra contains non-trivial closed ideals? And for answering this question, we will need some operator ideals. And the first operator ideal we need is a classical one introduced by Persson and Peach, quasi-p-nuclear operators, and here is a definition of this class of operators. So an operator U is quasi-p-nuclear if there is a sequence in X star, Xn star, which is strongly p-summable, so that this estimate holds for the norm of Ux for all X. Okay, and these classes of quasi-p-nuclear operators, they are operator ideals for every p between 1 and infinity. And we have this monotonicity, so Q and P lies inside Q and Q, and they lie inside the compact operators whenever P is smaller than Q. Now here are two results on quasi p-nuclear operators that are relevant in this talk. So the first one is one by Davis and Johnson. They say that if X is superreflexive, then the quasi p-nuclear operators from X to Y are always strictly smaller than the compact operators from X to Y for an arbitrary Banach space Y. And there are some other results in this direction by Botello, Pellegrino, and Rueda. The next one is important for us. So this is a result by Reynov. Namely, there are reflexive Banach spaces X and Y, and a quasi p-nuclear operator from X to Y that is not approximable. And what this suggests perhaps is that one might find examples where the closure of the quasi p-nuclear operators will be a non-trivial closed ideal of the compact operators. We will also need the dual operator ideal of the quasi p-nuclear operators. So this is the class of Sinha-Karn p-compact operators. So this is a class introduced by Sinha-Karn, 2002. Okay, here's the definition. So an operator T is Sinha-Karn p-compact if we have a sequence Yn. is also strongly p-summable, so that T of the closed unit ball of X lies inside this kind of set. This is what they call a relatively p-compact subset of Y. And we have this similar monotonicity for the classes of Sinacan p-compact operators. And the most important thing for us is that we have this duality. So an operator is Sinacan p-compact if and only if its adjoint is quasi-p-nuclear. And it holds also the other way around, but we won't need that fact. Here is just a small remark. So this class of Sinacan p-compact operators was originally introduced by Sinha and Karn as p-compact operators. Well, we have kind of a little bit changed the terminology and notation for distinguishing from the historically earlier class. There's an earlier class of operator that was also called p-compact operators, which were introduced by Peach and Fourier and Schwarz in the 70s. So just to make that clear, and there are a couple of approximation properties related to this class Sinha-Karn p-compact operator that has been studied actively in the past 20 years, and we will also need one result from those investigations. So here is now another example which uses this operator ideal approach. So if we have P and Q, they have to satisfy these conditions here. Then we can find closed subspaces X of LQ and Y and Z of LP, so that if we take the direct sum W, then the closure of the quasi-p-nuclear operators will be a non-trivial closed ideal of K of W. And by duality, the Sinha-Karn p-compact operators, the closure will be a non-trivial closed ideal of the compact of W star. In particular here, if P is bigger than 4, we can choose Q to be P. So then we get a closed subspace W of LP, so that this one here holds. And let me also mention that for subspaces of C0, we can get both of these closure inside the compact operators on a closed subspace of C0. So there is a closed subspace X of C0, so that the closure of the Sinha-Karn p-compact operators and the quasi-p-nuclear operators will be two incomparable closed ideals of the compact operators. Okay, I will just to kind of show some of the techniques we have used. I will briefly sketch a proof of this first result here. So that the closure of the quasi-p-nuclear operators will be a non-trivial closed ideal of the compacts. Well, what we need here is a result by Choi and Kim about the P approximation property. So they show that there is a closed subspace of LQ, where Q now has to be satisfy the condition that's bigger than 2P divided by P minus 2. So they show that there is a closed subspace that fails the P approximation property. And then there is a duality result that yields that also the dual X star will fail the P approximation property. So this closed subspace here is actually the subspace constructed by Davy. And what this means is that there is a Sinha-Karn p-compact operator from a suitable Banach space x0 to x star that is not approximable. And then by duality, T star will be quasi-p nuclear. Then we use a classical result by Persson and Peach. So because T star is quasi-p nuclear, we can factorize this as BA through a closed subspace Y of LP, where, well, B can be compact, but in particular A is quasi-p nuclear here. And note that A cannot be approximable, because if it would be approximable, then T star would be approximable, and that would imply that T is approximable, which it is not. So E is not approximable. And then we use a result in our paper. So actually for any P not equal to 2, we can use this Batchellis factorization to construct a closed subspace Z of LP and a compact operator S, so that all the powers of S to the power n, they are never approximable. And now what we do is we simply take the direct sum of x, y, and zeta, and then this operator A here, this will yield an operator in W that is quasi-p nuclear, and it's not approximable. So we simply use the matrix notation, put a 0 everywhere else, and then we put A in the 2-1 component in the matrix. So we get this strict inclusion here, and then we use this operator S, which shows that also the quotient algebra AW will be non-nilpotent. So S will in the same way yield an operator, a compact operator on W, so that all the powers are never approximable. And this implies that the closure of the quasi-p nuclear operators lies strictly inside the compact operators. Well, why is this? Well, the quotient closure of Q and P divided by the approximable, that's nilpotent. So this is a classical fact that also goes back to the paper by Persson and Peach. So these classes of quasi-p nuclear operators satisfy this kind of Höller type product rule, and this implies that whenever you have a quasi-p nuclear operator U, then for sufficiently large M, the power U to the power M will be a quasi-2 nuclear operator, and the quasi-2 nuclear operators are always inside the approximable operators. And by approximating, we also get the same result for operators in the closure of the quasi-p nuclear operators. Okay, now of course we want to ask what about the case when P is less or equal to 4? Can we then find a closed subspace X of LP with a non-trivial closed ideal of the compact operators? Well, this we cannot do, unfortunately. And here, for instance, for the case P less than 2, we need something else than the quasi-p nuclear operators, because they always are, when P is less than 2, they are always inside the approximable operators. Okay. Next, I will perhaps just briefly comment on this example with 8 non-trivial closed ideals. So this goes to the setting of theorem 1, where we have a Banach space X with cotype 2, Banach space Y with type 2, and then we take the direct sum, and we will get 8 non-trivial closed ideals. Perhaps to save some time, I will not go into the details here, but we get 8 non-trivial closed ideals, and that's kind of the best we can so far do in this setting of theorem 1. So here I have counted the closed ideals we get, and perhaps this is more illustrating this picture here. So we get this kind of a diamond shape where a line indicates strict inclusion from left to right, and if there is no line, then the ideals are incomparable here. Okay, I guess I have a few minutes left. So as a final example, I will present an example where we have infinitely many closed ideals in the quotient algebra AX. This is in some sense the most elementary in the sense that we don't need that many results here, but this is perhaps a bit surprising, this example. So first of all, if we fix a P has to be in the reflexive range, and we take any Banach space X that has the approximation property, but the dual fails the approximation property. So such Banach spaces exist. Now, a fact or a result by Grothendieck implies that then there is a Banach space Y0, so that the compact operators from X to Y0 are strictly bigger than the approximable operators. But because X has the approximation property, then the compact operators from Y0 to X are all approximable, and also the compact operators on X are all approximable. And now what we do is we take the direct sum of xk, where x0 we define it to be y. It should be y not here, sorry. Yes, and xk, when k is bigger than 0, then we simply put xk to be the Banach space X that has the approximation property, but where x star fails the approximation property. And let's denote the natural projection onto the kth component by pk, and natural inclusion from the kth component to the direct sum by jk. And in a similar way as in for 2 times 2, or for direct sums of 2 spaces, we can use this matrix notation also for the space zeta. So we get an infinite matrix, which will in this case look like this. So the compact operators on this direct sum zeta, they will look like this. That only on the first row we have something that is not approximable. So every other row, all the components are approximable because X has the approximation property. And in particular, from the second column forward, all these K's here, there are compact operators that are not approximable in these components here. And now what we do is we define for any subset A of the natural numbers a class of compact operators IA in this way here. So we have that the C0 component is approximable, and also the 0S component is approximable for every S in this subset A of natural numbers. So here is an example. If A is the set with only the number 2, then this class will look like this. So what is changed here? Well, here in the, okay, here is the 0 column, here is the first column, here is the second column. So here we have an A. So here all these components are approximable. And one can show that these classes will be closed ideals, and they will be strictly between the approximable and the compact operators. Then also, if we take the quotient map, then we get closed ideals of the quotient algebra. But here in fact, these closed ideals will be nilpotent. And furthermore, we have this reverse inclusion. So if A is contained in B, then the corresponding closed ideal IB will be contained in IA. And here is an interesting fact. So these closed ideals IA, they are not closed ideals of the bounded operators for any A subset of the natural numbers. So in other words, we have a countable family of non-trivial closed ideals of the compact operators of Z, which has the reverse partial order structure of the power set of the natural numbers. And this means, by taking the quotient map, that the same is true for this family. And this will also be a nilpotent family of closed ideals of the quotient algebra. Okay, I guess that was all that I have to say today. So thank you all for your attention.
Thank you very much for the talk. That was very nice. Are there any or comments? Niels, go ahead.
Thank you for a very nice talk, Henrik. That was very interesting, and I'm sure my colleague Garth Dales, although he's retired now, I'm sure he will, I mean, he's still mathematically very active, and I'm sure he'll be excited to see these results, although I'm not sure he's with us today in the talk here. Anyway, what I wanted to ask you is, because you asked sort of for Banach algebraic methods for producing ideals. And it seems there is a very simple-minded one. Well, it may be difficult to carry out in practice, but as soon as you have identified a closed ideal that is strictly between the approximables and the compacts, then you just take an operator in that ideal that is not approximable, and you look at the ideal it generates. That will give you a new ideal, well, a new closed ideal if you take the closure, right? And well, it will be either it will be a new ideal in the sense it will be strictly smaller than where you started. That will be interesting because it gives you a new ideal, or it will be equal to the ideal you started with. That will also be interesting because that shows then you one of these sort of naturally arising ideals is actually singly generated, and I would consider that quite surprising, to be honest. So is that something you have looked at?
Well, we have thought about that possibility. Yes, yes. In either way, it would be an interesting result, but we don't have any results in that direction. Yes.
Sure. No, I can imagine this could be difficult to carry out in practice. Of course, you could also try it. I mean, you could try it with perhaps a finite subset of such operators if you wanted. I mean, that might give you better chances of generating the whole closed ideal you started with, but sort of to look for how many operators do you need to generate it, right?
Yeah, yeah, that's true. Yeah, but so I said we have thought about this possibility, but we don't have any results.
Sure. Thank you.
I have another question. Kind of. Can you say anything about the cardinality of this ideals, of the ideals? Can you say something? There will never be finitely many, or there always? I mean,
no. I mean, this is. We have these examples with very few closed ideals, but
yeah, yes,
it's by no means a classification of the closed ideals. So
yeah.
And
so you don't have any lower bound or upper bound.
No, that
other than
that we don't have as well.
Yeah.
I have a question. You hear me?
Yeah.
Yes, I hear you.
Yes. Thank you for the nice talk. I got the email last night and I looked up your paper. I hadn't seen it before. Excuse me. So you mentioned in the paper that, actually you mentioned in the talk that this result of John is not well known. That if your compact operator factors through a reflexive space without the AP, with the AP, then
yes,
then it's approximable, and that this yields as a corollary that there's no universal operator for non-approximable operators. Am I getting that right?
Yes.
You didn't mention that in the talk, but that was in the paper.
Yes, that's true. Yes.
Yeah, that was interesting because so we put that in, as you mentioned in your paper, we put that in as a problem. Ryan Cossey and I put that as a problem in another paper we had a few years ago. So anyway, thanks for pointing that out. It was not.
Okay,
there's. Yeah, there it is. So as a corollary, you can see that there's no universal operator for non-approximable operators, while there is one for compact operators.
Exactly. So, yeah. I could have mentioned that in the talk.
Oh, no, that's fine. You had a lot of things to say, but I guess you generated other operator ideals. I suppose you didn't look at the possibility of there being a non-universal operator for the complement of those operator ideals or anything like that. It seems to me that it's hard.
Yeah, we didn't look at other operator ideals, so we just put it came kind of as a bonus this result that non-approximable operators do not have a universal operator. Yes.
I think there was a sense when we were looking at it that you were going to have to do something very hard, and we have to learn things about non-approximable operators, and we're not really sure.
Yeah.
But I guess that was wrong.
Yeah.
My library doesn't have for some reason we can't get Mathanolan, which seems a bit strange. Or we have to get interlibrary loan, and perhaps that was the reason that I didn't look at the paper. But thank you for pointing that out. It was good to. I was reading it in my bed on my phone last night. I'm like, oh my God, they solved that problem. And then I'm looking and I see that it's just a corollary, and I'm like, okay, well, there you go. So thanks.
Yeah, it was perhaps surprising that it it came quite easy. Yeah.
All right, thank you. Any others? Okay, so thank you very much, Henrik, again. I'll stop recording.
Thank you.